In this lecture, I want to talk about the idea of an improper integral, what that is, and how we compute them. I think this is kind of an improper that's kind of implies something that's wrong, or at least kind of weird. It's improper. I'm not sure exactly where that terminology came from, but all it means is that we're going to be looking at an area under a curve that is got in the where we're integrating over an infinite length. So, for example, if you look at this red shaded region here, so this is the function 1 over x. We know it has an infinite discontinuity at on the y-axis, so it runs parallel to the y-axis going upward forever, right? So they never intersect. This area, well, we don't know. So the question is whether or not the area is infinite, but we know that going upward on the y-axis, it's never going to the curve will never touch the y-axis. So it's never going to be kind of a closed area. It'll always be open in the sense that it'll keep on. There will continue to be area between the curve and the y-axis. And likewise, if we look at the blue area, if we started at 1 and we went to infinity, then again, 1 over x never actually, the limit is 0, but it never actually reaches 0, so they don't intersect. There's going to be kind of this open space between the function and the x-axis. And again, the question is the area there finite or infinite? I think our intuition might say, well, if the length of the interval is infinite, then the area must be infinite. And so why are we even having this discussion? But actually, that's not true in many cases. In many cases, we can integrate over an infinite interval and still end up with a finite area, which is a little mind-boggling, really. So that's what we're going to look at here. How do we even write that? How do we write like an infinite length or interval? So let's take a look at this red area. You can see if this is, so I've basically divided right at this point here at at 1, 0. So we have one integral over here, one area, and another area over here. So the red area we could describe as the integral from 0 to 1 of 1 over x dx. But of course, 0 is not in the domain of 1 over x because 1 over 0 is undefined. So the way that we're going to write that, generally when we look at a general integral, right, we'll go like from a to b of f of x dx. So we're going to replace the lower limit with a. We're going to go from a to 1 of 1 over x dx. So let's say, for example, let's just say a is right here, right? Then we'd be looking at this area right here. And of course, that area is finite because it's closed. So what we want to do is we want to let a move towards 0. So we're going to take the limit as a goes to 0 from the right, right? It's approaching 0 from the right-hand side. So ultimately what we need to do is, by having now an actual definite integral, I can plug in a and I can plug in 1, where I couldn't plug in 0 before because it was not in the domain. Then after that, the resulting antiderivative, then I can take this limit. So we know that the antiderivative of 1 over x is natural log, so I'm going to have limit as a goes to 0 from the right of natural log of x, evaluated to a and 1. Maybe move this up here a little to get to the next line. So we've got then the limit as a approaches 0 from the right of natural log of 1 minus natural log of a. Natural log of 1 equals 0, so it's just a matter of evaluating this. So what does natural log do as a goes to 0? Well, it goes to negative infinity, right? So if you think about the graph of natural log, so this is going to be negative infinity and negative infinity. So this is going to go to infinity. So one thing I should point out here is infinity. A lot of students like to use infinity because we have the symbol for it. They kind of use it as a number and plug it in and do arithmetic with it. But infinity is not it's not a number. It's not something that obeys the laws of arithmetic. It's an idea. It basically means unbounded, right? So we have to be careful with that. So this basically just says that this area is unbounded. It's not finite. Okay, I don't want to belabor that. So we can see, and this is called, so when it goes to infinity, we say that the integral diverges. If the area is finite, then we say it converges. So let's take a look at the blue one. Now, that one, this area here, we could describe as the integral from 1 to infinity of 1 over x dx. All right. So something similar here. I'm going to replace that infinity with a b, the upper limit, and I'm going to let the limit as b goes to infinity, integral from 1 to b of 1 over x dx. All right. So same antiderivative, just different limits, right? So I'm going to have the limit as b goes to infinity of natural log of x from 1 to b, so that's going to give me the limit as b goes to infinity of natural log of b minus natural log of 1. We've already said that equals 0. And natural log, as b goes to infinity, the area underneath natural log also becomes infinite. It increases without bound. So this one diverges also. At this point, you might be wondering, I thought you said that some of these might converge, the area would be finite. Well, that is true, but unfortunately for 1 over x, it doesn't matter whether we look at this area between the y-axis and 1 or the area from 1 to infinity. In both cases, the area is infinite. Let's look at some other examples. Alright, so here I'm going to look at 1 over x squared. What if we basically evaluate the same integral that we did a moment ago, except now I'm looking at 1 over x squared. So I'm going to rewrite this as the limit as b goes to infinity of 1 to b. I'm just going to rewrite that as x to the negative 2 so we can use the power rule. So I've got limit as b goes to infinity. So this is we're going to add 1, divide by the new, right? So that's going to be negative 1 over x, and we're evaluating at 1 and b. So that's going to be the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. So again, the limit only applies to the part that has the b in it. And we know that if we take negative 1 and divide it by larger and larger and larger numbers, then this whole thing is going to go to 0. All right? And then, so I'm going to have 0 minus negative 1. That equals 1. So as crazy as it seems, so again, let's just draw this. So this is going to look very similar to 1 over x squared. Let's say that's 1. This area, going all the way out to, well, forever, that area is 1. Where if we did it with 1 over x, that same area is infinite. So it's, again, kind of mind-boggling, but notice the difference in the antiderivatives. The antiderivative of 1 over x was natural log. And if you think about natural log, the area, as you approach, not the area, but the function value as you get close to the y-axis goes to negative infinity, and if you go along the x-axis forever, it goes on to infinity. It's unbounded. What about if we did the same thing, but we wanted to look at this area, just to get a different color. What about over here? Is that area also finite? Let's take a look. So same function, different example, right? Or different integral. So we're going to go from 0 to 1. So this is going to be the limit as a approaches 0 from the right, a to 1 over x squared dx. So let's kind of just jump right to this step here because we know what the antiderivative is. So the limit as a approaches 0 from the right of negative 1 over x from a to 1. So I'm going to have the limit as a approaches 0 from the right of negative 1 over 1 minus negative 1 over a. All right, so let's just focus on this. What happens as a goes to 0? If it gets smaller and smaller, and we're dividing -1 by smaller and smaller and smaller numbers, that's going to go to -infinity. I'm subtracting -infinity, so this is going to, when we say equals infinity, what we just mean is that we can make that area as large as we want just by taking values of a closer and closer to 0. So, in this case, it converges because it converges to 1, and in this case, it diverges. Okay, so we see then that something happened here from 1 over x to 1 over x squared. So now, here I have a finite area, but this part is still infinite. Let's look at another example. 1 over the square root of x. And let's look at from 0 to 1. So, again, the graphs of these are all going to look fairly similar. This is kind of hyperbolic type graph here. And again, we're looking at from, so if that's 1, we're looking at this area right here. So let's, again, we have this infinite discontinuity, so we're going to replace that with a. Let a go to 0 from the right, and a to 1. Let's just rewrite this as x to the -1/2 dx. Using the power rule, we add 1, divide by the new exponent, so we're going to get 1/2 divided by 1/2, so we're going to get 2 x to the 1/2, or 2 square root of x. At the limits a and 1, at the limit as a goes to 0 from the right, and this is going to give me, let's see, 2 times the square root of 1 minus 2 times the square root of a. Okay, so this part doesn't have any a in it, so we can just rewrite that as 2, and if we look at this limit here, so we're going to apply this limit here where we have an a. As a goes to 0, then the square root of a goes to 0, and that's going to be minus 0, so we just get 2. So this converges. Alright, so we have a finite area here. Let's again take a look at what happens out here. So, so we're looking at the integral from 1 to b, limit as b goes to infinity of 1 over the square root of x. So let's kind of jump down to this point. We know what the antiderivative is. The only thing that's different there are the limits. So we're taking the limit as b goes to infinity, 2 square root of x. We're going 1 to b. So this is going to be the limit as b goes to infinity, 2 times the square root of b minus 2 times the square root of 1. Well, we know that's equal to 2. But what happens to square root as the number underneath the square root goes to infinity? That also goes to infinity. This is going to go to infinity. So this diverges. So let's just take a quick look here to compare. So when I did 1 over x squared, this area from 1 to infinity was finite. It converged. But the area between the y-axis and 1, and also I should point out it doesn't really matter where we pick here. We could pick 1, we could pick 2, we could pick 1/2. The issue is the fact that the left hand is getting closer and closer to the y-axis. That's what made it diverge. And then it flipped when we had 1 over the square root of x. Then this area was finite, but this area was infinite. So I want to kind of just give a picture example of why that would be. Let's see if we can get this here. Alright, so I have this function. I'm not sure if you can maybe zoom in here a little bit so you can see. So here's 1 over x. And what I've done is I put in a slider, this n, for the exponent of x. And notice then what happens if I move this, if I make it bigger, look at what happens. It moves down closer. It closes down that space between the function and the x-axis. So when I get bigger than 1, so it doesn't have to be, like even like 1.6, 1.7, you know, 1 over x squared we've already done. So this area right in here becomes finite, and the area between, the y-axis and the curve is infinite. And then if we go the other way, notice now when I make that smaller, the curve moves away from the x-axis and towards the y-axis. Sorry, I'm spitting all over the place. I'm so excited about this. Okay, so that's what happened with the, we can just see as we change the exponent, and as we get less than 1, that's where we're going to close down that space between the y-axis and the curve enough that that area becomes finite, where the area between the curve and the x-axis becomes infinite. So let's just go back and summarize that. Let's see here. Get a fresh piece of paper and just summarize that idea here. So if we're looking at, I guess I need to back this up again now. Whoops, other way. All right, so if we're looking at the integral from 1 to infinity of 1 over x to the n dx, all right, so we're looking at something like this area right here, if this is 1, then that converges when n is greater than 1. All right, and that's for anything greater than 1. It could be 1.1, 1.01. It's when we get down to 1 that the antiderivative is natural log, and then we have a problem. Whereas if we're looking at the integral from 0 to 1 of 1 over x to the n dx, all right. So at that point, we are looking at this area right here. Then that converges when n is less than 1. And I should say, I can add to this, this diverges when n is less than or equal to 1. This diverges when n is greater than or equal to 1. So as I said before, 1 over x kind of gets left out of both. It diverges regardless. But in other cases, it could converge. We could have a finite area.